I'm Jonathan Coe. I'm here to talk about allocator-aware type design for library components. You can see our cover slide has beautifully captured some of the ominous weather we see outside. We can see the dark clouds. So yeah, unusually prescient. I think last year's one was sunnier. Yeah, coincidence maybe. Cool. So just a quick outline what we're going to talk over. So I'm going to talk about the motivation, why we actually started looking at allocators in the first place. So a friend and I have added some new types, or I'm in the process of adding some new types to the C++ standard, and we were invited to add allocator support to those types. Rather than dwelling on those more complicated types, we're going to use a simple type, dynamic optional, din optional I've called it, for the purposes of this talk, when we'll implement dynamic optional without allocators. Then we'll have a look at allocators. Then we'll use the Lego analogy we developed for understanding allocators ourselves. And then we'll revise dynamic optional to add allocator support. Some of the sample code is missing bits, like it's meant to be slideware, so it's made as simple as possible. Hopefully no simpler, but yeah, some bits might be missing. So yeah, we've been working on adding these new value types along with Sean Parent and Peacock. I've worked on adding these to the C++ standard. These are two class templates. They're designed for use as components of classes, and they have value semantics. So indirect is a bit like unique pointer, but behaves like a value. Polymorphic is a little bit less like unique pointer, also behaves like a value, and that supports inheritance and the like. So you can put things inside a polymorphic object which are of a derived class. So you can have a polymorphic shape inside your picture class, or a vector of polymorphic shapes. And then you can put squares and triangles and circles inside your vector of shapes, and the correct destructors and copy constructors and things will all be called for you by the compiler. It uses a little bit of type erasure inside. It's a little bit finicky to implement yourself. Without allocator support, indirect was pretty easy to implement, so it was arguable whether it was worth standardizing or not. But with allocator support, it becomes messy enough to make it worth standardizing. But we're not going to dwell on these types. I've already spoken about them at C++ on C in the past. If you want to see more about the work in progress, it's on GitHub and also in flight in papers in the committee. So we're going to look at a much simpler type, that's dynamic optional. So dynamic optional is sort of a very lazy optional. Just like optional, it either has a value in it or it's empty. When it's non-empty, then the value inside it is stored in dynamic memory, hence the name dynamic optional. I can't think of any sensible reason why you'd actually want to use this in your code. It's great for my examples. If you have a motivating reason for coming to use this, using this class, come and talk to me afterwards and I can hopefully persuade you not to. So dynamic optional without allocators. So we've got this, it's a template class, so we have a single template argument, our type name t, and then we've got a pointer to that t inside. We've got a default constructor, which will create an empty optional. We have a forwarding constructor, which lets you build an optional with something in it. Then we've got copy and move constructors. We've got assignment operators, and it didn't all fit on one slide. We have operator bool to see if there's anything in there or not. And then we've got const and non-const accessors. We want, like optional, this should behave like a value, so you want const and non-const overloads for accessors. We have a modifier, and then we have a destructor. And if you're really going to use this class, well, first of all, don't. But if you're really going to use this class, there's probably a host of other methods you want, functions you want adding, and they're not in here. So yeah, but for slideware, this is good. So let's go through and just implement these. So default constructor, there's only one data member, which is the pointer, so it just sticks the pointer into a null state. Not much more to say there. The forwarding constructor will create a new t object. The pointer then points to that, and it will create that t by forwarding those constructor arguments. All so simple, hopefully. And then we have a copy and move constructor. So for the copy constructor, we check that the optional we're copying from has actually got something in it. If it doesn't, then we just can create an optional in a null state. If there was something in the other optional, then we copy the object in the other optional. This requires the optional object to be copy constructible. The move constructor is similar, but we don't bother checking to see if there's something there or not. We don't care. We just take it and then null out the thing we moved from. we have some assignment operators. So we have a copy assignment, which does a similar dance. First of all, we check to see if we're assigning to ourselves. If we are, we don't need to do anything. Then we check to see if there's anything in the object we are assigning from. If there's something to copy, we copy it. If there's nothing to copy, then we don't copy it. And the move constructor, as before, move assignment, just like the move constructor, doesn't bother checking. It just takes hold of the thing that was in there. And if it's null, then you're null. If it wasn't null, then you've got the thing that was in there before, and you null out the thing you moved from. Again, with the check to see you're not assigning to yourself. Operator bool, perhaps as expected by everyone in the audience, you just check the pointer's non-null, nothing to it. And we have our accessors, which just return the pointer or the dereference pointer. And then non-const accessors will do the same, but with the const gone. We have member swap, which is called swap on the two pointers. Not much going on there. And the destructor, which will delete the pointer. So, yeah. Well, first of all, if we wanted to implement this ourselves, I'm confident most people in the audience could have a go at implementing dynamic optional without reference to my slides. It's not really a very complicated class, in which case I've won a little victory by finding a suitably simple example. But suppose you want to do clever things with memory allocation, which is why we're here. So we've used new to allocate memory and construct an object. So if you recall, we had a few little bits of code which had putter as new something. And then we use delete to destroy the object and deallocate the array memory. But if we want finer control over memory allocation and deallocation, and in fact, maybe we want to divide the construction into object creation and allocation as separate things with different levels of customization in different places, how do we do that? So earlier on in designing indirect and polymorphic, I didn't put allocators in. I put these, they had custom copiers and custom deleters in there. So custom deleters came from the unique pointer, which has already got a deleter in it. And copiers, well, unique pointer doesn't have a copier because it can't be copied. But I thought indirect and polymorphic could support this notion of a custom copier. And that actually got quite far through standardization. I mean, it got up to C++20, and then I had a conversation in the actually library wording group with Marshall Clow, and we thought, you know what, maybe these types aren't quite ready. Maybe we need to revisit the allocators after all, because there's nothing you can do with the custom copiers and deleters that you couldn't do with the allocators, and there was a whole bunch you could do with the allocators which you couldn't do with copiers and deleters. So we were right to pause. Anyway, allocators. So according to Bjorn, he'd probably know, the basic purpose of an allocator is to provide a source of memory for a given type and a place to return that memory once it's no longer needed. So allocators will give us a more granular way to manage memory than simple new and delete. And as I said, separate allocation and construction and deallocation and destruction. So new does both allocation and construction, and delete does destruction and deallocation of memory. I hope I've got that right. So allocators, as John was in fact telling me earlier on, were added to C++ as part of the STL. They weren't part of Stepanov's original design. They were put in by the committee who wanted a way to support near and far pointers, I think. And they look like this. So vector has for instance, has an allocator as its second template argument, and that defaults to the standard allocator. And before C++11, there's not really very much you could do with them. Allocators were quite lightweight handles. They had a bunch of member functions on them, and those member functions would be called to do things. And it was assumed that those member functions would be accessing some global memory resource. So C++11 changed that quite significantly, with a lot of work from Bloomberg, making allocators stateful. And as the allocators became more complicated, it was desirable to find a neater way of interacting with them. Rather than relying on them having a whole bunch of potentially redundant member functions, they use these allocator traits. So, but yeah, why do we want allocators? Well, my early answer to that was I didn't. I wanted copiers and deleters, but actually they can do things you can't do through other means. So allocators will let you do things, for instance, like rather than relying on the heap, you could take a big chunk of stack memory and then use that within an allocator to allocate memory for some little local computation you're doing. If you know all the objects are going to be in a certain context created or destroyed by the same thread, then you don't need locks on the memory resource. So you could use a thread local allocation to speed that up. You can use local memory pools to make sure that chunks of memory are allocated together where they're going to be used together, make things more cache friendly, get more relevant information into a cache line. You can avoid memory fragmentation by allocating small objects in one pool and large objects in a bigger pool. And I've, in the process of developing reference implementations for indirect and polymorphic, written plenty of debugging and instrumentation level allocators to sort of print out what's going on and when it's happening. And relocatable data and shared memory. So memory shared between processes will need more complicated pointers, and that can also be supported by clever use of allocators, which will support these things called fancy pointers. Okay. Any questions so far? I'll take that as a no. Speed. No, sorry, that was completely implicit, but yes, speed. Like, yeah, speed. So the top one, speed, thread allocation, speed, local memory pools, speed, arena allocation, speed, debugging, instrumentation and testing, speed of development, and relocatable data and shared memory, probably speed as well. It's probably all speed. That's essentially what we're all here for. But it's a great question. Yeah, I should have mentioned speed. That's why you do anything, right? Okay, so while in this beautiful place, we were working on adding allocators to indirect and polymorphic, which in hindsight we probably could have started a little bit earlier. And we're working on the reference implementation. We had the wording kind of like in a good state, and we're working on the reference implementation. And I came up with this Lego analogy, and then started explaining this Lego analogy to Ant, and explaining how it made everything really clear. And then I realized that actually our implementation didn't really work under the Lego analogy. It appeared to be doing some quite strange things. And then we wrote some more tests, not for the Lego analogy, but for our reference implementation. And we found that all the places where the Lego analogy and the reference implementation diverged, the tests failed. So I began to think maybe this analogy is actually quite useful. So I'm going to share it. If you don't like it, then don't use it. So in our Lego C++ model, the Lego bricks are bits of memory, and our object is the model we're making from the bricks. So bricks come out of the pile to build a model, and when you are finished with it, or so my mother says, they should go back into the pile and not be left all over the floor. As your Lego pile, as mine certainly did as a child, grows, it becomes larger and larger, and finding the bricks becomes the time-dominating process. So the bricks are kindly sorted out into different colored boxes, at which point it's very important the boxes that are the bricks that are red, which came from the red brick box, when you finish using it, they go back in the red brick box. Otherwise, you will return to the anarchy of before. So yes, things come out of a specific box and back into the same box they came from. So when we have our model and then decide to extend it, so we want to add another turret onto our tower, then we have a choice. Do we use the same collection of bricks we used initially? So perhaps it's a well-defined Lego set someone's bought you, and it's got all the bricks to build that set, and then you decide you want to put another tower onto that set. Those bricks are going to have to come from somewhere else. Or perhaps you're building a red castle and you want a red tower, so the red bricks should be used again to add the red tower. But the important thing is bricks have to go back where they came from. So this sort of maps onto scoped allocators, where you have a hierarchy of containers, and you can opt into using the same allocator for all the containers in your tree. So if you imagine you have a vector of strings, and the vector is using a particular allocator, and it allocates memory for these strings, but then the strings are using a different allocator, then whatever win you were hoping to make by using the allocator for the vector is probably offset by the fact the strings are now using a different allocator. You probably want to use the same allocator all the way down. And if you don't, then your design is different to mine. Copying models. So there's a discovery I made in this slide, which is that ChatGPT is great at generating images, but it really can't deal with Lego. So if you look closely, the bricks are not quite right. It gets things wrong. They're kind of like the current day fingers, I think. Yes, so when we copy a model, we can use the same box of bricks as the original model, or we can use a different box of bricks. So if you went round to your friend's house to play, and they've got a nice house, and you want to copy their house, they might require that you use your bricks, not their bricks. Otherwise, you'll go home with some of their bricks, and that friendship may come to an end. That would be sad. So yes, important thing, as always, we make sure when the models are taken apart, bricks return to the correct box. Otherwise, we return to anarchy. Okay, my Lego analogy now ends. There'll be no more mention of Lego. So we want to make an allocator part of dynamic optional, and we'll use the allocator to allocate and deallocate memory. So goodbye to new and delete. The user can then specify the allocator they want when they create their dynamic optional. And just because we have no imagination, and probably because the design earlier for vector was quite good, we'll add the allocator as a second template argument and provide a default argument of stud allocator t. And then internally, we're going to interact with the allocator using the allocator traits. If there's one slide in this talk which has got useful information in it, this is probably it. So interacting with allocator traits provide you a pointer type definition. This may not be the same as T star. If you have fancy pointers, it'll be something different, but most of the time it will be a T star. So allocators, as promised, separate out allocation and construction. So allocator traits has a function called allocate, which takes an allocator and the number of things you want to allocate. The allocator traits know what your object is, so they know how much memory to allocate, and they will return a pointer to that block of memory. We then pass that pointer into allocator traits construct, which takes in the allocator, and then the raw address of the memory, which may not be the same as the pointer itself. So if it's a fancy pointer, there may be some jumping around required to get the actual raw memory address from the memory returned in the line above. And then we pass in whichever arguments we want to pass to the constructor. I've put stood forward use in there to make it generic, but whatever you want to construct it with. So since we don't know what this allocator is, it could be doing literally anything in construct. It could be calling a completely different function. Like why you'd want to do that, I have no idea. It's probably calling the constructor of the type one. That's probably what you want to do. It may be doing some other things as well, maybe using some logging, setting things up nicely. But you could define an allocator to just print out the constructor arguments and do nothing, but no one would use it. And then to get rid of an object, we call destroy. So we call destroy with the allocator, and then again the address of the memory, and then deallocate to free that memory up, which will possibly return it to the pool, but it might not. You might have a stack allocator which is just creating objects, and when you call deallocate doesn't do anything, and it just waits till the end of the stack lifetime and then throws it all away, so you don't have to do any popping on and off. I think John and I were talking about this earlier, and you can get some like insane speed wins from doing this. I haven't played myself. Allocator traits is wonderfully documented on CPP reference. So yeah, look there if you need to know more. So for scoped allocator support, we want to make our dynamic optional type allocator-aware. What that means is that when it's used in a container, if the container is using allocators, when it creates one of the objects it is able to create, it'll look at the object and say, sort of, do you need an allocator? And if the object wants to say yes, it needs to opt in by defining this allocator type def internally. So that will advertise allocator awareness to any container, which might contain an instance of your object. So as we found out, if you use this using allocator type equals allocator type def, then you've advertised allocator awareness, which means you have to implement a whole load of functions. And if you haven't done it, you get really confusing compiler errors out. And then you have to find people from Bloomberg really quite early in the morning in Hawaii to fix things for you. And yeah, so I've learned something. This is not innocuous. This really does something significant. Similarly, if you don't have this type def and haven't advertised allocator awareness, then it won't find your allocator extended constructors. Allocator extended constructors. What are those? So when we advertise support for allocators by using this, defining this using allocator type equals allocator, we're expected to provide allocator extended constructors. So these can be in one of two types. I've picked the second type because it's more flexible. You can either have an allocator, I've picked both. You can either have the allocator as the training argument, or you can have a leading argument of stud allocator argt and an allocator. The reason why the second one is around is in the case where you've got a variadic number of arguments at the end, there's no way it will work out that the last one is an allocator and that meant something special, so you sort of tag it. Which means having tuples of allocator argt is probably difficult, but this is a small price we pay for allocator support. And then, yeah, so allocator propagation. So when we copy or assign an instance of our allocator, remember my earlier story about going to your friend's house to copy their Lego house, whose bricks do you use? I did mention Lego and I said I wouldn't. So copying or assigning an instance of our allocator-aware type is controlled by these allocator traits. So we have this function called select on container copy construction, which will determine when we copy a container whether we create a new instance of the allocator or copy the existing allocator or do something else, although what that other thing would be, I'm not really sure. And then we have these three definitions. We have propagate on container copy assignment, propagate on container move assignment, and propagate on container swap. And those traits are all used to decide what we do with the allocator when we're copying, moving, or swapping. So all the machinery is now in place. So we'll add our allocator template argument to dynamic optional. And yeah, we've added our allocator extended constructors. So we can see we have our allocator in there as our first data member. It's got this tag on it, no unique address. So that avoids having to use this empty base class optimization, which is complicated to read and not very nice on slides. Essentially means if the allocator's got 0 size, so if the allocator had no state, it would have no size, and you don't want a stateless allocator to increase the size of your object. So this no unique address deals with that. And so we have these, the constructors we had from dynamic optional before, the default constructor and then the forwarding constructor. And then we've got two allocator extended constructors, which are just the previous constructors with allocator argt and then allocator passed in as leading constructor arguments. And marked down as
allocator stateless.
Yeah. It's, maybe I misunderstood the question. What was the question? The question was, is the default
The size is 0.
Yeah, so the stud allocator has got no size because all the resources come from some sort of global pool, and if you had like thread local allocators, they would similarly be stateless. It's only when you've got sort of a local memory resource. So if you had an allocator which was backed by stack, that would be stateful, and the state would be a pointer to the piece of stack you were using. Great question. So yeah, again, we need more allocator extended constructors. We need our copy and move constructor. We'll add allocator extended copy and move constructor. So again, that's just allocator argt, allocator const a in front of the arguments for copy and move constructor. And assignment, there's no allocator extended assignment. That would look weird. And there's no change to any of the rest of the functions in terms of interface. The implementations would be subtly different. So in implementing these things, it's quite useful to define a couple of helper functions. One second. So to reduce bloat of slideware, we have this construct function, which should be giving us some exception safety guarantees. So what we'll do is we'll use the allocator to give us a block of memory. If that failed, then we'll free up that block of memory and then throw an exception. If it succeeded, then we'll construct an object inside that block of memory. And then return that block of memory. So that gives us our pointer construct. So again, using allocator traits to do the allocate and do the construct. And those will be, as before, calling into your allocator to see if it's got a special function to do construction and allocation with. And if it doesn't have either of those things, it'll just call the defaults defined by allocator traits. And we similarly have a destruction helper, which does something pretty similar. This one doesn't have exception safety worries to concern itself with, so it doesn't massively reduce the amount of code on the screen, but it just calls destroy and then deallocate. So implementing our constructors with allocators, our default constructor. That's not right. No, it doesn't do that. Default constructor should put it in a null state. That is not right. Okay. The forwarding constructor is right. Forwarding constructor will call construct inside pointer, so that pointer now points to the a thing returned by construct, which has got these arguments forwarded to it. And the allocator extended constructors look much the same, but we're now passing in the allocator to the member data allocator to construct that before we use that to construct the object. And again, this is the same mistake made twice. So the default constructor shouldn't be doing anything with putter. Putter should be null, but the forwarding constructor is fine. It's all much clearer when it's bigger. It's a shame. I need a bigger monitor at home. So copy and move constructors. Here we use this select on container copy construction to decide what to do with the allocator. And then we use the construct helper function passing in the allocator to construct a new object if there was something in the object we're copying from. And if we're not copying anything, then it just goes into this null state. And the select on container copy construction, which takes the allocator as an argument, is in all likelihood either going to create a new allocator, a new default constructed allocator, or copy the previous allocator. I don't know what other options would really be available. For move construction, the allocator always gets copied, and then the pointers are just exchanged as we saw before. So that one's not really much changed, other than we do something with the allocator. We have allocator extended copy and move constructors. So this slide should contain a few surprises. It's pretty much the same as the previous one, but we're now passing in allocator argt and an allocator, and then using that allocator to construct our allocator. And the same for the move. Okay, for copy assignment, this is where things unfortunately get a little bit complicated. So propagate on container copy assignment. So we'll check that trait and see if we should be copying the allocator when we do a copy assignment. So if there's nothing to copy, then we'll use our existing allocator to destroy the existing owned object. So the reason this is difficult to write is you can't look at the propagate on container copy assignment and immediately update the allocators, because then you run the risk of destroying an object which was there with the wrong allocator, and that's putting blue bricks back in the red box, and yeah, Lego again, but works. So yeah, so we'll check to see if there's nothing in other. If there's nothing in other, then we need to use the allocator we originally had to destroy the object we own, if there was an object. If there is something to copy, then we'll create a copy using the allocator that we will own. So either the existing allocator, if allocators are not propagated, or a copy of the other allocator if allocators are propagated. We'll create a temp, and then we will destroy the object we own with the existing allocator. Then we'll take ownership of that temp object we created, and then depending on the status of propagate on container copy assignment, we will update the allocator. So copying allocators and assigning allocators is essentially free. They're pointers or empty, so nothing's going on there. Okay. And similarly for move assignment, so we have a different trait here. This is propagate on container move assignment. So if there's nothing to move from, we'll just destroy the thing we have, and then we don't need to worry about keeping track of allocators. Otherwise, if the allocators are equivalent to one another, then we can just swap them over, and we can just swap over the pointers. So that's not too bad. Otherwise, if the allocators aren't equivalent to each other, and yeah, if the allocators aren't equivalent to others, so there's some state in there, and the allocators don't compare equal. Moves actually not that simple to implement. We're going to have to create a new object, because it's important that the object we get rid of is got rid of by the same thing that created it. So if we just switch objects around, then the wrong allocator is going to clean things up. So this is super finicky to get right. And then at the end, as before, we'll check to see if we had to update this allocator, and if we did, then the allocator gets updated. And then for swap, swap is the nastiest of all of them, unfortunately. So we use propagate on container swap to determine how allocators get handled. So if we have propagate on container swap, then we swap the allocators and we swap the pointers, and that's all fine. If we don't propagate on container swap, but the allocators compare equal, well, if the allocators can compare equal, then they can allocate and deallocate objects from one another because they're the same resource. In which case you just swap the pointers, that's fine. Otherwise, it's actually undefined behavior. In the standard, if you take a vector and another vector, and they've got allocators which don't compare equal to one another, and swap them, then that's UB. You're not meant to do that. So we have stood unreachable in here. So for collections in the standard library, swap's not allowed to invalidate iterators, and the only way to do that is to make swap if you don't propagate allocators, and allocators are not equal, undefined, which was a surprise to me. And the destructor is thankfully really simple. You just call the nice destroy function on the pointer, and it's all gone. Okay, so in our limited defense, slideware. Do not use our example code. We have willingly and knowingly omitted assertions, which there should have been some of, requires clauses, which we definitely should have had some of, static asserts, which might have been nice, no except, definitely needed, const expr, all the things. We left that out. Explicit, probably could have been in there. No discard, we discarded it. And any sort of helpful comments whatsoever. I'd like to give thanks to my co-authors, in fact, Antony Peacock and Sean Parent. Sean sadly didn't make the slides for some reason. Nina Rands for fielding my endless video call questions on allocators. Everything I know really has been the first order taught to me by Nina. Joshua Byrne from Bloomberg for pair debugging, that horrible bug with the using allocator type thing I mentioned. Neela for help with the slides and presentations. Bob Stegall for his awesome cppcon 2017 talk on allocators. If you want to learn about how to write an allocator, go watch that. It's great. And then assorted members of the C++ community, largely Bloomberg, I think, for their ongoing excellent work on allocators. We've been the grateful recipients of a very great deal of wisdom, and all the mistakes are our own. Thank you.